I am going to start recording. So first few weeks, we just briefly talked about some of the data content, some of the ideas on how to leverage different tools to pivot and get on here. Going forward, starting literally this week and last week, we will be doing something that is more on the analytics side, and we'll talk about what that really means going forward. I just want to this is something that is that was supposed to be done on your own time last week, week 3. But I just wanted to just want to kind of review and go back and talk about some of the foundational building blocks that we will be using as we get into the beautiful world of analytics. So last week we talked about a lot of different, when I say last week, last few weeks, we talked about data. Um, and then last week 3, we talked about information. And now we'll be slowly climbing that data value chain ladder, eventually talking about analytics in next few weeks, and then decisions, actions, and values. So eventually, the idea is that whatever you do, it has to have a purpose and it has to add value. And value could be from a revenue generating side, more revenue. Could be if you're looking from a safety side, it could be creating a more safe environment for the workers. And the value could really depend on the organization you're working for. It has to have foundational, fundamental change. And today we'll be talking about how we can use the data to make information, and that information will serve to become something called insights. And the insights is what our tools that can we use to create value. So just trying to quickly go through last few weeks, last week rather, is that we can get a lot of information from everyone. Like, data is at the purest form, um, some raw component, and it's a factual component. It's something that is observed and that happened, and it could be in your textual format, structured format, it could be hybrid, it could be unstructured like multimedia and so forth. Eventually that data needs to be turned into information. And what is information then? Information is something that is now controlled. Information is something that is ready and primed to be taken to a next step. Information also could be now setting up for you to ask questions. So just having a bunch of Excel sheet is in theory not information. That is data. You need to put it in a proper portal. You need to put it in proper engine. You need to set it up so that it can answer a bunch of questions. Now it becomes information. And to understand this information, there is this school of thought called Bloom's taxonomy. If you have um, somewhat been in either teaching environment, be it at a more post-secondary or even sooner, or anywhere, if you are taught at some point, you must have kind of come through this school of thought. It's called Bloom's taxonomy. And if you notice your learning outcomes, if you notice your course outcomes, if you notice your program outcomes, any program you're taking, any program you're taking, they will be using words like remember, understand, apply, analyze, evaluate, and create. So this is almost a 100-year-old thought process. What this is telling you is that there's two ways of thinking or approaching content or information. You can remember, understand, and apply. Those are lower order thinking skills. And analyzing, evaluating, creating, there are higher order thinking skills. The first half talks about a lot of memorizing, just understanding, just kind of getting into thick of things. The second part, higher order, really forces you to investigate a little deeper. So this goes beyond this course, to be honest. The Bloom's taxonomy, if you note, now going forward, if you really wanted to choose another program, let's say, you're always improving yourself, you really want to kind of get into the habit of always upgrading, upskilling yourself, and you really want to know what entails if I took another program, for example. Most of the course developers are using this framework. You can actually apply this not just in an academic environment, but also when you're writing, user documents, training materials in your organization, because it's telling you that there are two levels of thinking. So now, why are we bringing this up? There is no distinction there is distinction, but there is no preference over one or the other. Lower order thinking is set up for certain areas that might be applied. I mean, there could be components, there could be environment where you just need to understand. You don't need to create or evaluate or have a super critical thinking. But if you really want to go deeper about the analysis of data, you need to choose the higher order thinking skills. So just, if you're ever curious, and you can go back to this program and this course, they should have a lot of words like this. Create linear regression model. That is forcing you to do some critical thinking. Understand linear regression model. That's totally different content. You were just understanding their applied component of it. So even when you're looking data, you can choose if you want to go lower order of thinking or higher order of thinking. The world, the analytics world that we work in, typically higher order thinking is more preferred. We also talked about framing questions. I mean, this goes on and on and on and on until you end this program. This will keep on coming back. Simple way to look at it is, eventually, if you want to add value to the organization, you do need to know exactly what you're solving, what the problem is. If you do not have a clear path to the problem or a clear definition of the problem, what are you even solving? It just doesn't make sense. So we talk about during the course of this program is that a good problem is very defined, specific statement or question that has multiple outcome variables, that has, in some ways, there's a lot of variables. What I mean by is, like, if you wanted to fix problems of, generating more revenue in Walmart, for example, as opposed to saying, find all information about Walmart, revenue about Walmart, that's a very unclear question. A good question could be, provide me revenue of Walmart by state or by province, by location, by product, and so forth. Many, many qualifiers, many, many variables that are enclosed in that business questions. So you can have a lot of views. You can have a lot of different areas that you can look at the problem. So it has to be clear. So, I mean, we have to get in the mindset that as we go traverse upwards to the data value chain, we need to ensure that those questions are clearly defined. So we're still in week 3, and this is I mean, you can go back and go more in depth, but essentially I'm just doing a quick review. In week 3, we spent some time about descriptive analysis. We really started. Hopefully you had a chance to go through the lab, week 3 lab. If you didn't, that's perfectly fine. The video that I posted for week 3, just follow along. It should take you 10-15 minutes. It just trying to get you comfortable with the Python environment. So once again, we had data. We turned that into information. So it's an organized, structured of data. When I say structured, I don't mean structured data, but organized data. Structure is the wrong word to use. Those information should be turned into insights. And what are insights? Are patterns. If you look at the sales of, soccer ball in Walmart, maybe there's Euro 2024 that is going on. Maybe there are more soccer balls being sold. Maybe that's a pattern that you can observe, right? On that note, as we go through, there's another whole awesome domain of time series analysis. I'm just going to type it here. That is, if you are into supply chain forecasting, this is something that you should really have under your arsenal. If you're working in a lot of retailers, this is something they do all the time series forecasting. So there's a lot of different analytical model, which again we haven't even touched, but really I just want to throw it out there is one if you wanted to make a distinction, one is it has no temporal or time element. There's no essence of time. We don't care about time. That's one analysis. The second analysis is like there's element of time, like a GDP growth or sales in Walmart or international students in Canada. They have time element. Time is super important, right? So if you are into that domain, keep an eye out for time series forecasting models. That is super, super awesome as well. So eventually, the knowledge is creation or aggregation of information, data, information, and that was turned into some patterns or observation, some sort of, modeling or function, and that allows us to give or make some decisions. So now we have all these insights and information and data that says, okay, maybe now we are ready to make a move, right? So it's same thing. It's the next thing you can find is talking about the data from the left-hand side. We get that data and turn into information based on observation surveys, whatever we want to call it. We've structured that. We validate the model. Validate means ensuring the model is sturdy, and at the end, the apply and act is a domain where knowledge turns into um, value adding components of our analysis. We also talked about, the whole point of the pipeline, right? So as you can see, and I've mentioned it a few times already, is that the idea of turning data into some sort of insights and eventually adding value. Most of the work is sourcing the data, cleaning the data, structuring the data, and so forth. Think about this way in your real life, right? If you wanted to find some information about something, you work in a Walmart, you wanted to find information about soccer shoes being sold in June, for example. Even at a very big organization, you need to go through different stakeholders to get that information. Maybe there's someone who's taking care of vendor information. Maybe someone there's looking at more from a sales point of view. And if you wanted to create a model, you need to speak to a lot of these people. And I'm just throwing random example here, but the point I'm trying to make is integration, cleansing, preparing is good 70 to 80% of your work most of the times. So this is why the leveraging of Python becomes even more beautiful, because it allows us to do a lot of automation. This is not to say that Excel or any other tools are less competent. Excel is super powerful. And if you wanted to be an Excel expert, that sounds like pretty awesome, because more than 2 billion people in the world use Excel. If you really wanted career aspiration using Excel, do you want to be like super master? That's a good tool, because there's always going to be need for people for you to help them out. But Excel is application heavy. It is not suitable for a large amount of data. It cannot automate as well as some of the scripting languages, because you have to open that application on your computer. Every time you open that application on a computer, it's taking about, I don't know, close to a gigabytes if it's a big file. The memory is what I'm talking about. It's laggy, it's slow. If you ever opened an Excel that is more than 100,000 rows, you might as well make yourself a nice cup of tea or coffee, because it's going to take time. But if you're using things like Python, it just expedites the process. So the point I'm trying to make here is, the process view is encapsulating of three bottom blocks: data, information, and analytics. So what is analytics then? Or analysis. So someone says, you are like a data analyst or some business analyst. What does it mean? Well, at the purest level, analysis means that you are decomposing or breaking down in larger concepts into simple, simplified version. If you have a uh, if you really wanted to see how car works, you have to take them apart. You have to see where the engine is. You have to see where the brakes are. You have to see where the door closes. So that, in essence, at an abstract level, you need to take them apart. So analysis is really going through each and every component, whatever you're doing, modeling, generating some reports. It's about fragmenting, decomposing, breaking down into smaller pieces. Synthesis, on the opposite side, is taking important parts and combining that for a bigger picture. So both of them serve different purposes. Our goal here is to leverage analytics so that we can better understand our approach. We can better understand and see what are some of the variables that are important, and maybe that will allow and give us some competitive advantage. So just very quickly, some sort of analysis that could be done, statistical analysis, which we focus here, and we can do diagnostic, local optimization, on the synthesis side, design thinking, global optimize. So we focus more on the analysis part here. So maybe a question to you now is, let's say if you are wanting to analyze something. If someone told you, hey, listen, this is an Excel sheet of sales data. Analyze, give me something, give me some feedback on this. What's the first thing you would do? This doesn't have to be, just think about it. If someone gave you some information, what's the first thing you would do? And you can throw it on chat if you wish, or you can open your mic, whatever works for you.
Hi, sir. Hi.
Yes,
We try to minimize the field and understand what the fields in the data in Excel files, how many rows in Excel files, and find the best field and unique field to find out their queries.
Yeah, I mean, there's that's absolutely correct. You try to find the data types. You try to see how many observations there are.
Yes.
You try to see just to kind of get comfortable with data. That's perfectly good approach. First up is what else?
Generally, other than the way that, you perform analysis, there is we run pivot tables, trying to summarize the sales data.
Yeah, so very good point, Adil. Thank you so much. Is the pivot table gives us representational context to the data. So if you have thousands of rows, perhaps you can pivot and see the clusters. Perhaps you can see some of the mean modes, things like that. So it just gives us extra information. Now we're going a little deeper, right? Because information at 100,000 rows of observations is overwhelming. And one of the things we need to do is understand data, like Lavjit said and Adil said. Try to put it in a pivot table to see a lot of different things. I'm just looking at the chat here, and someone says, probe more. What exactly are they looking for? Yeah, that is perfectly fine. Find the problem and then understand. Okay, that's also fine. So the first thing, and this is never a wrong approach, whatever you're saying is correct. But when we are going into world of analytics, the first thing we always do is something called descriptive analysis. And whatever you said is correct. I mean, this is what it is. Descriptive analysis is understanding historical context of data. If someone gave you Excel sheet full of sales data, you want to know what happened in the past, first of all. I mean, to your point, understanding data type, understanding the structure of business problem, those are absolutely correct. There's nothing wrong with that. But let's say we know those things. What's next when it comes to analysis? We want to know the historic context. How are we going to project, predict, forecast if we do not have any idea about the current data? So always, 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 we do something called descriptive analysis. And if you have numerical data, you can try to find the mean, median, mode, range, variance, standard deviation, outliers, histogram, bar chart, percentiles. There's many, many different tools, not limited to just these ones. But the idea is, if you have sales data, now you have some idea. What is the mean sales? What's the median sales? Right? You will get some context on this one. So the first thing is always looking at descriptive analysis. Naturally, your question is, what happens to the text? Let's say you have free text. I mean, yes, not always everything is going to be numerical or categorical. So there's a way to do descriptive analysis on categorical data as well. Perhaps you can do clustering. Perhaps you can do sentiment analysis. Does anyone know sentiment analysis? Let's say you go Google review, right? And I am a business owner. And my business is very dependent on the reviews people are putting. Obviously, people will, Google will ask people to rate you like 4, 3, 5. That is different. That is perfectly fine. But perhaps as an owner, I also want to know what are some of the phrases people are putting consistently. Maybe they're saying the food is awesome, but the washroom was not clean. And they're giving 3.5. Yes, you got 3.5, but you don't know why you're getting 3.5. Or maybe there's one particular item that is constantly telling you, constantly decreasing your rating. So that is a wonderful world of text mining, sentiment analysis. So you can actually look at, and there's really cool, algorithms. I'm happy to, I did a bit of research on that as well, and I'm happy to share my knowledge at some point if you wish, but it's really cool. A lot of times people use free text, meaning that they'll be sending or putting a lot of content. And that is not numerical. It's really hard to quantify those things. But there are techniques now that we can parse through a lot of different data using a lot of different algorithms, and it will give you insight. Perhaps for me, I can make that quantitative. Maybe I'll just say, find all the words that mean terrible and give me for last 5 years, and I can see the trend. Now you can turn into more descriptive analytical data. So there's a lot of different tools. So the first step we always do is descriptive analysis. And we also talked about, and this is something that was from week 3 that you should have found, is essentially what I'm trying to convey here is that for you to do descriptive analysis, you can use a lot of different tools. I earlier in the course, I posted some SwiftViz and Y data profiling, some Python tools. So hopefully you'll be able to use it. But there's something called DataViz catalog. If you want to create certain types of chart, you would just go in here, and it will tell you some description about the chart, some explanation. Oops. And then if you wanted to learn how to generate this visualization, you can just click depending on your Python programming. So for you, you'll be here. So one of the cool libraries that I use is Plotly. And it's the beautiful thing is, like, let's say at work you want to create something, and most of the work now they allow Python as an environment. So just ask them around, like if you're not working in this environment, and a lot of times the technology is quite restrictive, just say, hey, is there a package that I can download that is allowed, and you can do these things. So for example, if you wanted to create a chart like this, like let's say bar chart, and bar chart, you would just go here and you see that thing, it is giving you the code. Now you can just manipulate this code and figure it out, right? So a lot of times the code is already here, right? So you can just learn things like, so Plotly is amazing. It's free, it's open source, although it's just pricing that it is indeed free. The other one is Seaborn as well, same thing. There's a different libraries. I go through these in tutorial as well. Just give it a look, if you wanted some cool chart, there's a code here. It'll tell you exactly what. So these are the variables that you can change in the quotation and so forth, right? So, just try it out. The best way to learn is imitate someone. I truly believe that is someone has something, and you can just imitate and try it out and be unique and so forth. It's really hard because at the end of the day, programming is someone else's work anyway. All you're doing is being creative with someone else's adding on to that. So don't feel too worried that it's copying pasting. But you do need to know, okay, let's say if you wanted to change the style, where do I change these things, these variables, and as you go through it, you'll learn, right? So a lot of times the documentation will tell you some information. So everyone has a GitHub. You can try it out. Some people are very responsive. So for example, one of the beautiful parts of IT community is that you'll get responses from people. Like you can go to Stack Overflow, Stack Exchange. If you're unsure, just post your code. It's like a forum. People are very, very helpful. Now you also have generative AI, Copilot, ChatGPT. Use it, obviously. There's nothing wrong with using generative AI, but be mindful that you know what you're doing, because if you're just copying and pasting, it may help you a little bit, but even if you're copying and pasting, understand what you're doing. Like, okay, this means that it's importing library. I get it. You should be able to tell what's going on. So that was week 3. That's all we covered, really. But feel free to go back and go in depth. But today we'll be going into something called analytics, and this is a bit of a pathway from last week. So as you can see at the bottom, the red little box is moving up, and our learning outcomes. And if you note, can someone notice a specific style of writing on the bullet points? Does it ring a bell? Like if you read the learning outcomes of this or learning objectives of this week, does it ring a bell? Did it cover a concept that we kind of talked about very early on? Okay, so let's see, right? Define, analytics, distinguish, understand, describe. Let's go back here, right? So if you notice here, it's kind of like talking about these higher or lower road thinking. So it's always anything we built in the academic world, or even learning material. Most of them are leveraging Bloom's taxonomy. It's like they're like a religious book almost whenever they're designing. So you can very quickly tell that by reading the learning outcomes, describing, understanding. So it looks like it's mostly lower order stuff. And eventually we'll go into higher order stuff at some point. But anyway, to summarize it, we'll do statistical analysis with Python. That is the intent. And again, the video is already posted. And we'll try to understand what are we even analyzing and how we're analyzing. So again, the first part of analyzing is always going to be descriptive. Describe the historical data. And second is something. And third is something. So we'll continue to build on that. So when you're doing a project or anything, in your at your free time, this is going to be your step: descriptive, inferential, predictive, diagnostic, and so forth. It's slightly different terminologies, but it means more or less the same thing. So there's a bunch of topics introduced here. Statistical analysis, different ways of doing it. We're also going to slightly touch in probability. and exploratory data analysis is another one. So, you know, we'll gradually move through different steps. So once again, what is analysis? Yes, we said that analysis is idea of breaking down, but analytics using the same virtue is using statistical and quantitative analysis to really explain data, predict data, and make decisions. Now, my question to you is, why are we hearing about AI and machine learning all of a sudden? Like, why is that? Like, you know, looks like we all knew basic principles of mathematics, even from the past. But why do you think it is all of a sudden more prevalent and prominent in today's world? Throw it in the chat if you wish to contribute. Anyone? Why do you think the chat? So Iris says increased demand for convenience. Absolutely, for sure. What else? Amount of digital data available. Okay, let's keep. Could lower the cost of production automation. All right, all good answers. But think about it, right? Like, yes, Judy has a good point. The development of modern technology, and it's interesting because now we're talking about statistics, and if you look at the statistics book, most of the theories that were incubated 5, 6, 7, 8, sometimes a couple of thousand years ago. So, you know, statistical analysis is something that has always been there. I mean, if you go back 50 years, there were books that were just as good. But what changed now are a few things. One is we have access to more data. And two, we have technology that can parse and action large amount of data in a relatively quick amount of time. That is what changed. So, you know, if you think that AI was incubated or generated yesterday, it's wrong, or a few years ago. The modern science, the machine learning component is like, if you go literature in 1950s, they talk about these things, but most of the time they had to use hand or manual calculation. It was impossible. Imagine parsing through millions of data and not making mistakes. That is quite challenging, right? But, you know, if you have like Python programming, if you have, you know, different scripts, different big servers, it is much easier, right? So that's what changed. So statistical analysis is, you know, and AI and mathematics and probabilities all are foundational knowledge for all the tools that we use. Your descriptive analysis is also statistics at a very rudimentary level. It's talking about mean, mode, median, range, variance, so forth, which most of us learn quite early on. So all it does is interpreting data, and what machine learning AI does is use that analysis, use that mathematical formulated conclusions, and apply it at a larger scale. That is simply, that's what's happening. So we are not doing anything new. We're just leveraging new technology to look at different like, you know, use cases. So this is what you will look at, and this is the types of analytics, and it is by Gartner. Gartner is a big research firm that predominantly works in IT sector, talking about emerging technology and technology in general. But the literature might be a little different in the sense that some may talk about you know, different wordings, but generally you'll find the first is descriptive analysis is hindsight. Diagnostic is why it happened, and we'll talk about that. And then predictive analytics is now you're starting to use the historical data to predict something. So think about it this way. there's a weather data, and you can tell that it rains a lot in June. And how do you know that? You ran descriptive analysis, mean, mode, median, whatever. Maybe you can answer why it's happening. Well, it's June. Looks like June. There's a lot of clouds being built up. It's hot. It goes, the clouds are forming and it can't take it anymore, and it releases the rain. Diagnostic. It tells you that. Predictive is now you are saying, looks like it's going to rain a lot in June. So maybe 2025 June, it's going to rain. You are going to predict. And the last part is prescriptive. Maybe we want it to rain in 2025. What can we do based on the data? So hindsight, insight, and foresight. And the value chain is, this is not to say is less value, although it looks like it, but really everything has value. But, as you go into the beautiful world of forecasting and predicting, the value is multiplied. So once again, descriptive analysis, historical data, and how do we conform, or how do you get that? We can use dashboards, reports, visualization, and also it is storytelling. This is where it's more fun, right? So this is just using the data and presenting in a way that it can be easily consumed quite quickly. It is least difficult on a difficulty scale. We can start diagnosing, and a lot of times we diagnose with hypothesis testing, assumption validation, ad hoc analysis. And what does it mean? Think about it, right? The COVID came along and they created vaccine. And when the vaccine was being created, they had a group A where they injected vaccines, and group B, they did not inject vaccines. And two groups, really. They looked at it and observed the physical condition of group A, the vaccines, and they observed physical condition of group B with no vaccines. For you to confirm that the vaccine is working, group A had to be significantly less sick or ill from flu. That is hypothesis testing. You put a hypothesis that saying that if you give vaccine to someone, they will not be sick, and alternatively, if you do not give vaccine to someone, they will get sick. So those are diagnostic analysis. Those are things that you can use to answer why. And the why answer would be because they have vaccines, they are not sick. So little difficult than descriptive, but more insight. Now we're starting to get into the idea of validating your analysis with some testing. The third is prediction. We love this. Prediction, no one has ever been, the funny thing is, like, we talk about AI and machine learning, forecasting. We spend so much time doing these things. But the sad thing is no one has ever become right or correct 100%. Whatever we do between now and end of the course, we are going to be wrong, as in inaccurate. There's no way we will be correct. How discouraging is that? But on the bright side, all we're trying to do is to be closer to being fully correct. We are closer to having some confidence, maybe at an 80% or 90% level, that we are going to be correct. That is all we're doing. And how do we predict? We're using historical data, obviously. And let's say the same rain example that I was giving you, I mean, if you're like, if your descriptive analysis is telling you that it's going to rain more in June, and why? Because it's going to be warm, and why? Because in its monsoon season in some countries, or why? Because we're, for whatever reason. Sorry, I'm not a weather expert, but you have those 4, 5, 6, 7 different reasons why, and you can use those why and what and to model a predictive analytics. So a simplistic modeling could be, it is going to rain in June 1st 50 millimeters because it did the same in June 1st 2024. The weather is going to be dark or cloudy. There's going to be thunderstorms. So you can add a lot of variables to create a predictive model. But can you for sure say that June 1st 2025 is going to be rainy, or it's going to rain a lot? You don't know that, but you hope that 90% or 80% or whatever percentage you think is good is going to give you that confidence that you are going to be probably be more right than wrong. But that is life, right? Because in predictive analytics, and naturally the question is, how come we have all this data, all these tools, and we can't be wrong? So, we end up being wrong. Why? Well, the reason being, and we call this epsilon in mathematics, is something like this. It's called epsilon, is that some things cannot be factored. It is beyond our scope. Think about it, right? Like, you see Michael Jordan's parents were both very short. His brother was very short. His dad was 5'7", and mom was, I think, shorter than that, like 5'6" or 5'5". He became 6'7", a foot longer. His brother, shorter. His sister, normal height. If I created a model based on his parents' height, there's no way for me to predict Michael Jordan's height, no matter how much data I had. Some things in life are very difficult because it is just difficult. It's just we cannot model everything. But we hope that when we are projecting heights of people whose parents are 5'7", 5'6", we kind of are accurate. We can say maybe they will be up to 5'11", or maybe 5'4", 5'5", but definitely not 6'10". We want to be in that situation given that data. So this is what the prediction is going to be on a historical context. Foresight or prescriptive tells you about what exactly needs to be done for you to achieve something. You can say, you can essentially, Michael Jordan's example says, like, if you want someone to be as tall as Michael Jordan and super awesome athlete as Michael Jordan, you should be, based on the historical data, based on the observation of nutrition from their parents, based on some of the stuff they did, you should be born in South Carolina, you should be eating, 5 gallons of milk, you should be having a lot of calcium tablets, whatever it is. That is prescriptive analysis based on the observation that we for descriptive diagnostic and predictive. Right. So, going forward, your analytics model is going to encapsulate all of them or some of them, at least descriptive analytics. Or sometimes this is also described as descriptive and inferential, right? So what does that mean? Is that descriptive is historical data, this part. Inferential is these things. You're inferring something from historical data. Based on CSDA 1100, based on the performance of the student for the last 10 years, I can infer that you guys are going to be awesome as well. I'm inferring based on actionable or historical data. Is it? I'll just pause here and open up if there are any questions. All right. Okay, so it is almost 50 minutes since we started. Let's take a 7 minutes break. 7. and we can be back at 10:30 sharp. Thank you so much, guys. So 10:30 sharp, and we'll continue to have a nice tempo going forward. So 10:30. Thank you. All right, we have a question on the chat, and Asmiya says, I have a question. What if the predictive analysis came to be true just 30 to 40% out of 80%, which was predicted earlier by analysts? So in what case, in that case, what analysts should do? Essentially, if I'm correct, what Ashima is saying is that if it's your model or your predictive tools are underperforming the analyst, well, in that case, you should always use whatever has the confirmed higher accuracy. So just because we put it through a model doesn't mean it's always going to be usable. So a rule of thumb is if it's showing 100% accuracy, it is a problem. If it's showing 50-60% accuracy, cannot be usable. A good Goldilocks or sweet spot would be 80 to 95% around that range, where you can be comfortable that the model is good. Anytime it's 85 and above, it's a usable model, because you're going to be right 85% of the time. That looks like a good number. Okay, I'm going to just quickly initiate a poll here just to get an idea and something. Oops, I think I made a mistake here. And okay, I'm asking a question quickly. Just I think save the library here and okay, poll should come up. I just want to get some ideas. The question is, do all of you know your group number? And I'll give 30 seconds. This is also an indirect way of collecting data on you, to be honest. So, I recently realized, well, not recently, but a while ago, when I was, going to these doctoral classes and they took attendance, and this is a way to grab data. So the Zoom, the backend stuff collects like how much time you spend and things like that. It's crazy. All right, so the end poll, I mean, this is just not for any surprises, but looks like 16 people know your group, so kindly continue to work. And because next week, by the time when we come back, you'll have to have your sprint one done anyway. All right, so let's get started. It's just to give an idea, because maybe I'm not putting the groups out there properly. Anyway, so let's move on. The analytics is something like, if you are a farmer and you want to maximize crop yield, what do you need? The problem first. I mean, what are you trying to find? And this has to be a very specific problem. In some cases, we also call it dependent variable. The things that you're trying to find out is called dependent variable. So eventually so for example, price of gas. If you're curious about finding price of gas, if you're curious about finding price of house, if you're curious about finding yield of a crop, these are called dependent variables. So you need to have dependent variable established very quickly. And the problem statement, it has to be specific. And a lot of people make it more complex. They say, oh, I want to find this. This is no. We need to be very specific on ideas, on things that we need to find. That's the first thing. After that, you need to source data. Well, that is also sequential thing is, maybe you need weather data, soil data, GPS drone imagery, and you can see it's multimodal data. You have some text, you have some CSV format, you have imagery, and so forth. And some of the analysis that we can do, or analytics we can do, is we can forecast rain, we can do some yield management, we can create some predictive models. So, it really gives an idea. If you want to, forecast rain, it will be a model that is strictly forecasting rain. So, with this information, you typically you can, either put more investment in the crops or less investment. Now it depends on you. The model is not going to tell you what it needs to be done. Really, it's up to you, but it just gives you that little tool for you to get forward. So learning from model, and this seems very, very, mathematical, but if you are somehow given, you get some sort of overwhelming feeling when you see the next few slides, do not worry about it. We'll have enough time to get back to that. But really, is that, the slope of a straight line, there's a function called y equals mx plus b. And let me draw this out so it makes more sense. Let's say this is y-axis, and this is x-axis. Anything that is vertical is going to be y-axis. Anything that is horizontal, that is going to be x-axis. Let's say you want to know housing price. Let's say you want to predict housing price, and whatever you are trying to predict always goes on y-axis. That's just a rule. Okay. So you want to predict the housing axis, but now you have historical data. Because remember, if you go back, until we have historical data, we cannot predict future. We need some context, right? So historical data says that, if your house is 1,000 square feet, if your house is 2,000 square feet, and let's say 3,000 square feet, you found data that if the housing is 2,000 square feet, the price is 500K, and so forth, increment of 1,000, let's say 1 million, and I'm just going to say 1.5 million here. So you found 3 observations, just 3, and you say every time the house was 1,000, this guy was 500,000. You mapped it, right? Because this is what you do. This is what the model does. And if it's 200,000, it was million. And if it was 3,000, it was 1.5 million. It's not a perfect example, but forgive me. So what this is telling you is that you can draw a line now, something like this, right? Let's draw a line. So what this is telling you is that as the square footage of the house increases, the price is also increasing. And this little function can be dictated by this slope function. For example, y is equal to slope of this little line, m, multiplied by this guy, x, plus b, the intercept. And intercept is right here. So, and we'll learn a lot in linear regression. So this is it. I mean, it sounds very complicated, but all we're doing is most of the times drawing these lines. Could it be possible that sometimes the house is 300 and it's a lot less? Of course, it can be possible, but very least you can see a trend and you can predict. Now, if someone comes to you and says, what happens if the house is 400 square feet? Then you'll say, oh, okay, looks like, my trend is telling me that it's probably going to be somewhere, which is going to be $2 million. So in some ways, this is a model. This is a functional model that we created very, very easily. Give me a thumbs up if it's somewhat clear. I don't expect it to be super clear, but very least it should give you some context on how you're doing it. Okay, so that's it. This is it. Like, it's like we think analytics is super complicated. No, it's very simple. And we'll just massage it, we'll just kind of tweak it a little bit, and eventually we'll get some context on this one. We can do a lot of different things with this. And this is all, eventually you're looking at descriptive analysis, and then you're just predicting based on the future data. So same idea, right? Think about this X is the, let's say, square footage, or whatever you want to call it. Negative square footage is not possible, but let's say there is temperature. So 0, 1, 2, 7, 3, -4, and Y, and we're saying Y equals 2x plus 4. So every time we build this function, we can predict the value of Y, right? So essentially, if you think about this as a temperature here, temp, you can say, and let's say this is like, Y equals housing price, house price. We want to know if the housing price is going to be, impactful due to temperature. So let's say if you want to say housing price, your answer would be Y equals 2 times 0 and 4. So if the temperature is 0, the housing price looks like it's going to be 4. If the temperature is 1, the housing price looks like 6, and so forth, right? So we created a model. And naturally, a question is, how did you even come up with this function? We'll talk about that in a bit. But the drawing of the line is like a fundamental thing. So just by knowing these things, you can actually predict, right? And this is what we call observation. This is what we call the data, right? This is what you're given to you, right? And based on this data, you'll be creating a model. So if you had to do the modeling for this one, you'd do something like this as well: Y and X, and you fill all the X's on this one, 0 all the way to 25. And remember, it's also going to be negative, so on this side as well. And then you will start plotting like this, right? And the line will be drawn like this. So that's the fundamental way of doing things. It's not always going to be positive, so the line is going to be drawn like this. So this is how we can just create a predictive analytics based on historical data. So that is how the equation comes along. We can come up with an equation to represent the data and arrive back at the original straight line, right? And this is something, what you call a linear regression, which we'll be working on it quite extensively in the next few weeks. So a linear regression will learn from the data, and it is quite a math-heavy concept. But what I'm trying to kind of give you some idea is that without you having access to X's and Y's beforehand, you cannot predict future, or you cannot predict what's going to happen, because without some context, it's almost insignificant, right? So that is why it is super important for you to realize that without some descriptive analysis, without some historical data, it's really hard to move forward. At a very abstract level, it is something looking like this. Inputs would be your data. The system is where you will have algorithms of your choice. I mean, linear regression is one algorithm. There's so many. And it'll give you some output. So to put it simply, grab data, structure it, decide what you want to do or what you want to find. Clean up the data. I'm oversimplifying here, but this is. Then use the algorithm of your choice, and which one, what one. This is something a longer discussion, but for now, just say choose an algorithm, and the algorithm will predict, and when it predicts, you can measure its accuracy, and if it's good, use it. If not, discard it. So that is typically how it works, and it's more or less, this is it. Some of our discussions will fall under trying to choose the right kind of modeling, and this is important as well as we go. Questions? Okay, I think someone's mic's turned on. Maybe there's a question. All right. So, I mean, these are just a bunch of words here, but what I'm trying to come across here is that this thing we created, right? This thing we created is a model. This is what we call a model. So when you say a model, it means that you learn from the past data, like, something like this, you learn from, and you have a function ready to go. So every time a real estate agent comes in and this is, hey, you have a model, right? And then you say, yes. Okay, the temperature in Manitoba is going to be 10 degrees. Can you tell me the housing price? So all you do is 10 times 10 plus 4. Looks like 24 million or whatever, 24,000. I think Manitoba is probably cheap. 24,000 is the price of the house. So this is a model building. And you came to this position by learning historical data, cleaning data, choosing an algorithm, assessing its viability and accuracy, and eventually saying that it is good for you to use. Okay, so I'm just trying to kind of re-emphasize the importance of having the right data over and over again. So model is representation or equation describing the relation between inputs and output. Model building is the process that we just kindly did. We map the stuff. And once the model is ready to go, all you have to do is feed data. Now, as the data changes, the model's accuracy also might change, because what if there's a different types of things that are happening? Or what if the model is not understanding well? So those are something as part of your continuous improvement that you have to look into it. This other world of, what I showed you right now is what they call is shallow learners in machine learning. Shallow means you give a number, it learns and it outputs. It's okay. It's not super smart. There's another term that comes now. It's called deep learning, which is, you hear it all the time, deep learning, artificial neural networks. There are many different things. The distinction here is that deep learning uses more sensors, more data to pretty much do the same thing, but it can process large amounts of data. If you think about it, right? If you are, let's look at it. Let's very quickly look at this example. If I do this, what is this? Throw it in chat. I drew something. What is that? Number 3. Okay. What about this? The second one, this is 3. What about this? Three. So you are not incorrect, and sorry, that's my dog on the background. But you are not incorrect. But how these look not exactly the same? But how did you know there's distinction, or how did you know all of them meant 3? Because they look kind of different, sizes different, almost different shapes. Obviously, they are similar in structure, but they are very different in some ways. If you give this to a shallow learner, it will have trouble understanding this, because it is looking at a very specific curves. If you give this to a deep learner, this is going to be super awesome, because it thinks like your brain. That is why it's called deep learning. In your brain, we have neurons, and the neurons are billions and billions of little light bulbs that captured a lot of different data. So a deep learning model will take this little piece and store it, take this little piece and store it. So it will take a lot of different information, and it can almost say that, wait a minute, it doesn't look the same, but it has the same curvature. Perhaps it is 3. So again, not to really get too deep into this, but really what I'm saying here is that deep learning mimics your neurons in your brain, meaning that your brain is much more powerful than any supercomputers out there. Our brain, for most of us, is absolutely thousands of times powerful than the best ChatGPT out there, guaranteed. There's no two ways about it. The only distinction between computers and us, and why it may feel like computers are smarter than us, is 2 things. One, computers are amazing doing repetitive things, repeating same thing over and over again. That's why I feel like, oh my God, these are smarter guys. And 2, computers are good at memory. They can memorize stuff. You know, if I told you what you ate 3 days ago, you'd have to think, but computer will be quick. So those are the only advantages that computers have. But in terms of the processing power of analytics, our brain is quite amazing. We see a lot of different things that supercomputers can't. So that is the distinction. So neural networks kind of like, trying the same concept of neuron is trying to capture more and more information. It is more applicable in images, where they can break down images into billions of pixels and store every data. That is why it's powerful. So, Crucial, so we have to make a lot of assumptions when you use model, especially the data aspect of it. It may induce some biases, because if your model is only trained on certain data, it will only predict something. If my students everyone is from Mississauga, Ontario, then my model will only give preference over Mississauga, Ontario. Let's look at another example. Previously, so in this model, we have a data, and the data says there's a customer ID, is, tenure, phone plan, uses, and attrition or attrite means if the person is leaving the company or not. If you look at this model, it has about 6 variables, and we're trying to predict if someone's going to leave the company or not based on this model. Sorry, Adele, you had a question. Go ahead.
Yeah, sorry, just a couple of slides back. So you mentioned that the ability of the models to actually remember. So does that actually also layer onto the Bloom taxonomy thinking style for AI based tools that, I mean, it can remember, understand, apply, analyze, evaluate, and create? That does that methodology also applies on?
Oh yeah, that's actually excellent question. So I mean, it's a complex thing. So if you look at it from a Bloom's taxonomy, it should be able to do most of the higher order learning, but it also needs explicit direction to do so. So if you do not program a model, if you do not program AI, it is not going to be able to just proceed and do it. And that is another higher level of thinking that we humans have, as opposed to the computers. There's this term called theory of mind. A theory of mind is eventually that your vacuum cleaner at home is smart in the sense that it can detect walls, and it can detect dangers that it won't tip off and things like that, fall off or damage your furniture. It is smart in the sense that it's gotten a lot of information, and it memorized it, and every time it sees a wall through the laser light, it will kind of annoy and things like that. But but it is not going to just one day and decide that it's going to start vacuuming, although you put a logic there and saying that at 9 p.m. it should do vacuum, but it is because you explicitly programmed. So although it may seem like it can do all those critical thinking, it needs explicit directions for it to do so. So not yet. There is a theory in machine learning AI is that eventually 60, 70, 80 years down the line, when the machines start getting really smart, they say that they will be kind of similar to or closer to humans, where if the vacuum cleaner does not want to clean itself, it will not do so. And the other part and the crazy part they talk about in sci-fi is that eventually they will start working against us because they have now more data, more intuition. But I don't think it'll happen in my lifetime, so I'm quite happy about that.
Makes sense. Thanks.
So, this is, if you wanted to create a model, now this is something called classification. So typically in machine learning or analytics, and one is something called regression. It estimates a numerical value. The second is classification. So it can tell you if the color of your car is red, blue, white, and so forth. And other was clustering. So, this is a little ahead of our thing, but I just wanted to give you some idea is that clustering is just, you throw it, like you throw data and it'll cluster, like, people who like samosa are going to be in one group, people who like burger are going to be in another group, and so forth. It will try to kind of figure that out on its own. But here we're looking at something called classification, and we're seeing classification is category, pass, fail, disease, not disease, black, yellow, that kind of stuff, right? So in here, if you wanted to predict if someone's going to leave the company, you need to tell them age, tenure, phone plan, and uses, and the predictive model will process based on the algorithm that you'll use, which we haven't talked about, and it will predict if someone's going to leave the company or not. Now, my question to you is, we're using age, tenure, phone plan, uses, but why are we not using customer ID? This is where critical thinking may be required. And maybe a hint here for you is that, customer ID, if you go to if you go to a new company, the chances are the customer ID is randomly created some random number. It really doesn't describe you. I mean, if you have 777, that looks like a good lucky number. That's just it. But someone randomly assigned that stuff, so it really has no inherent value to the model. So customer ID here is, you can just ignore it. Age, yes, it matters because age matters what stage of life you're in. Tenure matters. Phone plan matters. How much money you're paying. Things like that, it matters, right? The customer ID, your SIN number, your phone number may matter in some ways. That 647 or 416 means that you have had the number for a really long time. Maybe it'll matter, but some not all variables are treated equally. So in this case, you should not even care about these things. I mean, you could, but it won't make your model wrong, but it will just add another dimension to the data. Very quickly, this is something that we already talked about, and the only point I'm trying to make here is that data preparation, although Chris DM says it takes about 20 to 25%, I think in my career, at least 70 to 80% of work has been processing data. So this is just to building blocks, understanding. You talk about business outcomes, current state, some KPI definitions, and why, who, and how. You do a thorough assessment of what you're trying to do. Again, most of them are very obvious statements, something you probably are already doing, but this is usually the starting point. One of the biggest mistakes people make is trying to find data set before establishing a business problem. They're looking for data, and a lot of times when students, even in your sprint or a sprint, you're given a data set, but eventually when you do your project, don't go searching for data set first and come back to business problem second. That is counterproductive. So first establish the business problem, then go search for data. Obviously, I mean, if I want to know how many people live in the solar system, I mean, I don't have data for that. That's a hard problem to solve. But most of the problems we're trying to solve should have some data, or at least we can engineer and create data. So understanding of data. Now you starting to understand data. You look for data. This is where a lot of times, data engineers and data scientists clean the data, missing values, cleaning up, transforming, normalization, distribution, understand distribution, transformation, so forth. It is just preparing data. It's like, to look at a very simplistic way is 50 people, you got 50 different spreadsheets from 50 different people. Now, what are you going to do? Are you going to put everything in one spreadsheet? Are you going to choose a different file format and so forth? This is where it comes into play. And if you see the sequence of what, why, who, and how, we address or we put down the exact accountability. The modeling part is where most of the descriptive, diagnostic, predictive, and prescriptive comes into play. And this is where you'll be doing a lot of understanding of variables. So, the modeling part encapsulates all those 4 things we talked about, and it's primarily the job of a data scientist also. The last one is, yes, you create the model, but to someone's point earlier that you may have very weak accuracy, and which is going to be quite problematic, right? So when you have a problematic situations like that, you need to evaluate it first before you deploy it. It's kind of like same thing environment, like, in the software programmer runs stuff, it will have its own evaluation metrics on development environment before it gets to deployment. I think, when you are administering COVID vaccine, you probably have to, use some subjects to, put some, inject them and then see if it's going to be suitable or not before deployment. So again, data scientist, solutions, QA analyst, and so forth can, quality control analyst, and can look into this. And model validation, cross-validation means some terminology that are introduced. Is model validation just looking at how the model works in different data sets. Cross-validation means you are now using different kind of data to see what the error rate is going to be, and obviously testing, and also this also could be more of a qualitative evaluation where people question every part. So you have stakeholders where they talk about privacy, bias, ethics, suitability of the deployment, and so forth. And eventually, when you are actually ready to go, it becomes a model that is deployed. But the evaluation also gives feedback to the business understanding, because it's a continuous monitoring, and it should take a lot of different information that way. So Chris Dion, I mean, if you're ever getting into the area of building models, no one's going to sit there and say, "Oh, Chris Dion, this is something just good to know," really. But most of the thought process, most of the literature or school of thought kind of follows the same problem, or same style, or same sequence. So now we're kind of looking into a little more into data, because eventually we want to, let's say we have business understanding of what we're trying to do. Now we want to understand data, and the understanding of data comes into different ways. And one of the distinctions that you have to look at is the idea of quantitative and categorical data and so forth. If you have a model, and I'll go quickly back here. If you look at it here on the data, now age is a quantitative data, tenure is a quantitative data, phone plan is a quantitative data. Uses is a categorical data. It's a category: high, low, medium, green, blue, black, that kind of stuff. The last column is also categorical data: yes, no, good, bad, ugly, beautiful. Customer ID is a numerical data. Let's say if you put first row age in years, looks like that's years, 25, right? And the second row in month, then it will really screw the standardization of the data. So if you're doing in years, you have to do it in years throughout. If you're doing in months, you have to do it in months. If you're doing in dollar amount, you have to do dollar amount. You cannot have different types of data or different units of data. So to understand that, we need to understand some measurements data. So, how are you going to measure, speed of a car, 4 stars, customer number, just designation, temperature. All of these have to be standardized and scaled and consistent units of measurement. Within the, some distinction we have is ratio. You can also put ratio there. Comparing A and B, for example, that's a ratio. And if you compare A and B, and in the example I have on the slide is if if A is 10 and B is 5, A is 5 and it's bigger than B, or when it comes to delta, the minus. Or you can also look at it from proportion, where A is twice as B, which is the proportion. There's another interval, ordinal data. Ordinal data means that has something that has order. So, let's say a marathon runner, 1, 2, 3, 4, that is order, that came up as order. Nominal means color of the car, like, red, blue, black. There's no really order, it's just different, right? So all of these data can be configured in the model, and it will tell them specifically what kind of data it is when we're designing the model. And when we tell them that, it will process it accordingly. So what I mean by that is nominal data. If you have a model that is, and when I say model, always think about the spreadsheet that I showed you, like, a few rows. And if I put it there, it would not emphasize one over the other. So if I put red, blue, car, it will not say. But if I put ordinal data and I rank 1, 2, 3, 1 has a bigger value in the model. So, we have to be mindful of that. So these are some proportional things that, the ratio, the same thing I talked about is if you're comparing A and B, you can either do as proportional or a delta. The interval is, for example, that I have is the 0 point on the interval scale is not meaningful and is arbitrary, which means that, for example, if you're comparing A 5.0 and B equals 10, conclusion, negative B is twice as large as A, and it is incorrect to conclude anything of a proportion on an interval scale. We don't really use this too much, but it's something good to know. The ordinal measurements is, again, it's a ranking stuff. We can also do it, but typically it is less complicated than how the slides are showing you. Is that when you are defining the data types, when you're modeling, when you're putting into the Python, it will automatically understand different types of data. In some cases, you might have to explicitly program, but in most cases, if you put red, blue, black, it will actually know. If you do 1, 2, 3, 4, and you explicitly say it's an ordinal category, it will exactly know what it's looking for. So again, the same thing, it will also understand. So my point being is, without trying to memorize this, when you see the data set, and as we will be trying out, you will know exactly what the category is. In Python, if you have a data frame, like, for example, if let's say your data frame's name is df, then all you have to do is data types, and it should be able to tell you what kind of category it is already installed. And that is one of the things that we do in the lab as well. Hopefully you'll be able to find some time to do it. So moving along, basic statistics of analytics. And we talked about descriptive already, and inferential. So again, look, if you look at the bottom, this is descriptive, and this covers your diagnostic, predictive, and prescriptive. So inferential is just like a shortened version for those 3 things that come along. So again, we've talked about this already. First, describe the data. Now, once you describe it, you can infer some of the issues. So in example here, what we are looking here at it is something that really takes in account in modeling is random generation. And what we call a random generation or random phenomena is something that occurs, but we cannot predict it directly. But if we kind of do it over and over and over again, creating random, we can provide a trend, or we can see some sort of distribution or consistency or some sort of trend. Let's look at this example, right? Like if you, if let's say, if you toss a coin first time, can you be sure that it's going to be tails or heads? Well, it has 50% chance. There's no way to predict it. But if you flip the coin 50 times, and within those 50, after 50 times, you get 20 tails and 30 heads, then you now can tell that head has a better distribution or better outcome when you're running these experiments. So in this example, the red box that I see is random event, random phenomena is the tossing of the coins or trials. So 50 times is 50 trials. Each trial is independent. So, the first flipping of the coin has nothing to do with second, and vice versa. An event is a way to signify multiple outcomes. This is very brief kind of preview on the probability theory, right? So once again, we're kind of just throwing it out there, is that, this is just randomly I'm throwing out there, is once you have the data, the first part is descriptive analysis, and how we're going to do it is, again, the lab component covers it because it's applied. And then we slowly move on to the other parts. The other terminology I'm throwing out is EDA, exploratory data analysis. It's kind of like descriptive analysis, but you're really trying to understand the data. This even sometimes comes before descriptive. And sometimes you can also interchangeably use with descriptive. Like, sometimes people will just say EDA and then continue with their predictive, or sometimes people say EDA and descriptive. It's fine. You don't always have to have sections dedicated to this, but it just gives you an idea. But what it really does is try to understand what you're trying to do, or what kind of analysis that is possible. So one of the things the EDA does is univariate analysis and bivariate analysis. And without going too deep into definitions, let's do this. Let's say you have a data that has age, and then on one column, and the other column you have wage, salary of someone. And I'm just randomly throwing a number out there. Descriptive analysis, or univariate analysis, looks at this variable one at a time, these two variables one at a time. So it will just think about this age and think about wage separately. That is univariate. What kind of distribution it has? How does it look? The wage bivariate talks about relationship of age and wage. So and the relationship looks like, as the age is decreasing, people are getting more money. So univariate just focuses on one variable at a time, univariate. Bivariate talks about relationship of these two, how they are related, or dependencies, or relationships, whatever you want to call it. Something like this, Anscombe's quartet, it's we do it essentially. It's a summary statistics of a bunch of different variables. some of the things that we do from a univariate point of view. And this point here I'm trying to make here, sorry, I nearly forgot, is even sometimes if you look at these 1, 2, 3, 4 different sets of x and y's, they look very similar when it comes to the sum, average, standard deviation, but the charts look very different. That is why it's so important to visualize as well. That's the point I'm trying to make here. If you look at the sum, average, standard deviation, looks all the same, right? But if you look at the actual visualization, they look different, because sometimes the summary can induce a bias that we don't see. So it is so important to visualize it. In terms of univariate analysis, you can do something, and this is non-graphical methods. You can look at the central tendency of data, and central tendency is defined as where the data is clustered, or in other words, what is the mean of the data? What is the mode of the data? What is the leading characteristics of the data? And how similar are those data to each other? What is the shape of the data? Right? And shape, think about it this way, right? If I have age, right? And let's say age, I'm doing age here, and I have like a lot of data, let's say from 1 to 500, and I can map it, right? Like I can put something like a 1-year-old, 2-year-old, there are 10, 11-year-olds, 5-year-old, so whatever it is, I just plug it in, and this is what we call shape of the data, how it's looking like. It's just plotting. It looks fancy, but it's just plotting. So we're trying to understand where central tendency of data is. In other words, if you're using mean as a central tendency, where is the average is clustering around? That is something we want to know. So, we can use central tendency as mean, average value. Median means middle value, where 50% is on ahead of them and 50% is beyond them. And mode is the most common value. And we can use from there. We can also look at dispersion or spread of data. So variance, standard deviation, interquartile range. Standard deviation, and the best way to understand, to never forget standard deviation, is, let's say, this is the mean of the class. Let's say everyone got, the mean of the class is 80. And some people are perfect, they got 100 out of 100, and some people got failed and they have to take it again, and they got 40. Generally, what happens is those people are far and few, but people who are closer to mean are going to be a lot, and people who score the best are going to be low as well. So this is how typically data looks. It's mathematically proven. Right. Sorry, yes, Adele, go ahead, please.
Sorry, just a quick question. So the univariate can be called as a linear predictive model, or?
So univariate would be just one column of analysis. So if you have 10 columns in a data set, and
Yeah.
age is one of them, we're just understanding everything about age, nothing else. We don't care how age is related to anything else. We just care about the age.
Okay.
Whereas the bivariate or multivariate is, you're trying to understand how age is related to wage, because that's also important. So you want to know, so for example, univariate would be understanding you, just you. Bi or multivariate would be understanding relationship between you and me.
Okay.
Right.
Thanks.
So, just back to the point, is it kind of looks like that. And standard deviation essentially means that how far on average the data is from the mean. So if I'm telling you the mean is 80 and the low is 40 and the high is 100, does that give you a good impression of the data? it does somewhat, but it doesn't tell me everything. In other words, what if I had every student that got either 40 or 100? If I have every student that received 40 or 100, then average looks like it's nice. Average looks like it's going to be 70, but it's actually there's not a lot of people around here. So what standard deviation tells you is spread of data. And if you look at any documentation, if the standard deviation is really high, that means everyone's either people are getting really low or really high. If the standard deviation is small value, that means that everyone is getting very closer to each other. And as an instructor, that's what you want. You don't want people to get super high or super low. You want everyone to be around the same time. So that is just one way of looking at data. It's understanding data, that this is what we call is univariate thing, right? You can also understand sample. So mean, median, kurtosis, skewness is the shift of the data. We don't really need that for now. But if you look at it, the mean is 9.99 and standard deviation looks like it's okay. It's a lot of spread. It's not a bad thing. But if the standard deviation was 5, that means this would look something like this. This would look something like this. Very spread out data. Everyone's getting either low or either high. So we use histogram. And histogram is not your bar chart. What histogram is like, let's say if you have 1 million entries, you can tell histogram to create what you call our bins. These are bins, 1 bin, 2 bin, and so forth. You can say create 10 bins, and it will get 10 equal pieces, and it will say if the data is from 100,000 to 200,000, put it in 1 bin, 300,000 to 400,000 bin, so you can actually look at the distribution well. I go in quite detail in your lab video, so kindly, again, refer to that. It is one of the most first descriptive tool. Look at it. So if you look at this, looks like even without knowing too much statistics, you can tell that looks like a lot of people are around this area, 9.2 to 10.8, right? Because a lot of distribution is here. There are the lowest, lot less people are after 12.4 to here, and a lot less people are below 8.4. So it gives you some impression like that. Okay. Conversely, this is the red line is perfectly distributed data. It's a normal distribution. We'll talk about that more. But if it fits into that, it means the data is perfectly distributed. It's symmetric, right? It's been told that the attractiveness of someone's face is dependent on the symmetry of the face. So if you draw a line right between their nose, one side of the face should look very similar to the other side of the face. The symmetry is kind of important. The studies have shown. So, the symmetry is, good in data like this because it allows us to predict better. So, for example, if I'm telling you that, if this red little curve, the left side and right side are equal, then it's easy for me to predict. I'll talk more about that in a bit, but why is that important? But at least for now, we can analyze it if it falls or if it kind of conforms to symmetry. In some cases, when you distribute it, and again, these are all histograms, right? So these are all data that we plotted. This is an example of delay times of commercial airlines. Looks like, the airlines are either early or super delayed, delayed by over, 50 times and the frequency of 441, but it's not delayed 600 odd times. So, there's a specific window where it's delayed more. It looks like an hour, 2 hours, that kind of stuff. So its distribution is going to be kind of different. The other thing you'll be doing as part of, so we've done histogram as a descriptive analysis. We did, some described data, and we'll be doing something called box plot or box and whisker. It's also called. And this is a univariate example, right? So what this means is that, let's say this is age data, or rather, let's stick to the original example. This is the commercial airlines. So it will go and look all these data and create a box plot. And the box plot will do box. So this is a box, and this is a whisker is what they call, like cat's whisker. The way to read this is 50% of the data is going to be within this box. The black line is what we call a median. The right-hand side is maximum and left-hand side is minimum. So what is it doing? It is telling you distribution of data. And if there are outliers, for example, let's say there are outliers that do not belong to this data. And outliers are important because let's say you have 10 houses. 9 of them are priced from 100,000 to 150,000, and one of them is priced 1 million. If you use this 1 million, and you want to predict the house in Manitoba, for example, someone will say the mean price is like 200,000. This is giving you wrong information, because looks like most of the houses are 125, most bulk of it, and one guy comes in and just it creates that information, or creates that more stuff, right? So we need to identify outlier and take it out. There's no need. If you take this guy out, then you will have good representation of data, and box plot allows us to do that. And something like this is also min max. So there's one max. You can look at it, you can define it, you can also sometimes take this data out. Again, the box captures 50% of the data here. Histogram is based on the idea of to understand the shape of the data. So this is what you call the shape of the data. This is going to understand how your data looks like, and if you look on the right side, it's called absolute frequency and relative frequency. The distinction being that absolute frequency is like, let's say you have 100 people and you ask them to eat burger, and they tell them everyone someone ate -3 burger. Let's say someone ate -2 burger, someone ate like 4 burger. You just like draw it out. So that is absolute frequency. Relative frequency is percentage value, so it all equals to 1. So if there are 100 people that ate burger, if 5 people ate 1 burger, 5 people ate, the percentage of people eating 5 burger was 20%, 4 eating 25%, and so forth. And you will just map that, and obviously everything should be equal to 1. So this little things here, everything should be equal to 1. So it gives some representation as well. The shape should pretty much look the same, but it is slightly different way of doing things. All right, I'm going to pause here for a little few seconds. All right, so it is again, I know it's 11:28. Let's take a 3-minute break, 3 to 4 minute bio break, and let's be back at 12:33. I'll make it 12:33. If you're back. Thank you. All right, let's keep on going. So you can also use, you can turn category data into like histograms as well. It's not a problem. It will do a count of things that would appear, and then just leave it out as frequency as well. So this is an example of the absolute frequency, actual observation. The relative frequency, if you notice on the y-axis, is a numerical value which everything should add up to 1. So that is the distinction when you're doing it. The bivariate analysis that we're talking about is a relationship between x and y, or relationship between 2 variables. And what this means is, let's say, for example, I talked about housing, y, and price of housing, and x would be your square footage, right? And we charted something like this. The correlation, and it's moving towards from left to right, and it's trending upwards. And this is an example of a positive correlation. And what this means is that every time X increases value, Y's value also increased. Every time Y moved something, X also moved. So it is a positive correlation. A negative correlation is something if X moved by 1, Y moved by -1. It's moving opposite direction. No correlation means regardless of X does anything, Y is not going positive or negative. So correlation essentially is the relation between two variables to see their movement. Now, correlation does not imply causation. In other words, correlation, just because me and you are correlated, mean that that's not the reason. For example, I'll give you an example. Let's say at a beach, it is super warm, and whenever it's warm, the ice creams are sold more. That is a correlation. But you cannot for sure say that just because the weather is warm, ice cream is being sold. Perhaps there's a new flavor. Perhaps there's better marketing. That is, the causation could be something else. So yes, correlation and causation could be the same thing, but correlation essentially means going in the right direction. The square footage of the home and the price is correlated, but the causation really here is supply and demand and supply-demand, right? So we have to be very careful and understand the relation. But what this tells you is, correlation can give us analysis of two different variables. So a correlation coefficient is bounded, meaning someone's actually controlling it from -1 to +1. It cannot be 2, 3, 4, or it cannot also be -5. So a -1 is perfectly negative correlated. You walk one step to east, I'm walking one step to the west. That is perfect negative. I'm walking one step to the west, and you're also walking one step to the west. That is perfect positive. I am going east and you are going west. Sorry, I'm going east and you are going, not going anywhere. Are you going north, for example? That is no correlation. We do not have a correlation. Correlation gives us some idea. So, for example, in this chart here, distance and airtime are highly correlated, positive. And how do we know? You just draw a line. Looks like it is positive. If it was negatively correlated, it would look like this. If it was no correlated, it would look like straight. Think about it from a mathematical point of view is, as the distance increases, the airtime also increased. If there was a rocket ship that was going, regardless of distance, it was taking the same time, it would look like this, 200, no correlation. And if it was like, let's say, the time was actually decreasing as the distance was increasing, then it would be negative correlation. And, if you look at the correlation coefficient, is 0.97, which is highly, highly correlated. Okay. Questions, folks, on this matter? All right. So another example here is something that is a very low correlation, almost insignificant. It's all over the place, and you can figure it out. But the correlation coefficient on the lab will tell you exactly how to derive the number. We can also look at the probability theory, which looks into how probability plays into the thing, right? So earlier in the class, I talked about if there's a chance of raining on June 1st, there's a good probability that it will also rain at some point in next year. And we look at it probability to factor that. At the bottom, you see something called X bar. X bar means mean of the sample. And S means standard deviation. It's just a term or mathematical notation for it. So what is probability? Well, probability is exactly that, is that you're looking at what has happened in the past and you're going to assume the probability of it's happening again, the chance of it's happening again. The few things that we need to be mindful about probability is are there multiple different rules for it? And I will pause and I will create another little content for this one because it's a content that is quite mathematical, but really the best, simplest way to understand probability is relative frequency. Probability is always bounded between 0 to 1. So we surveyed 100 people, and out of those, 20 liked. Red car, 60 liked. Green car, and 20 liked black car. The probability of people liking green car based on the relative frequency is 60%, 60% or 0.60. So you can use this probability metric to make further projection. That is the simplest way to understand probability at this point. But within the probability, there are different rules. And the first, bias and variance, these are not rules, but these are some of the things that play into our thing. So for example, if that 100 sample size of cars would only encapsulate certain people you knew, your friends and families, that would induce biases. That will oversimplify things, that will cause some issues. Variance means that the amount by which an outcome prediction will change. For example, you create a model, and if there is different type of value, how will that model react? Bias and variance is a big trade-off thing that we need to do when you develop models. What I mean by that is bias. We need to ensure that we don't oversimplify models. At the same time, we also take into account of some unpredictable changes or shifts in data. Few terminology here, and there's no need to worry about memorizing these, but there's something called disjoint events or mutually exclusive events in probability. What does that mean? Think about it this way. You can be in Canada and you can be in the United States. The probability of you being in Canada is 50%, let's say, and the probability of you being in the United States is 50%. The mutually exclusive events is what it's telling you is that you cannot be at the same time. You cannot be at the same location at the same time. It is mutually exclusive. You can either eat dinner or lunch. You cannot be having both at the same time. So if it's for mutually exclusive or disjoint events, the probability that A or B occur, and the P stands for probability, P or AB, the probability of A or B should equate to you being in States and you being in Canada. So that should equal to 1 or the probability of both. It should all equal to 1. Disjoint events, again, once again, events that are completely independent of each other. They share no outcomes in common. The other one is conditional probability. What happens, think about the insurance thing. What happens if you have basement insurance? What's the probability of you having leakage? Not that insurance has anything to it, but just for argument's sake. Let's say you did, the probability of you having a leakage if you have recently redone your basement. So conditional probability is another thing that we do. And independence, like again, for the mutually disjoint, is two events are independent if the fact that one event occurred and does not change the probability of the other. And if you ever think about it, it's think about being in two places at the same time. There's certain probability that you'll be in Canada this year, and there's certain probability of chance that you'll be in vacation somewhere else, but both of them should combine to one. So once again, the probability is something that is 0 and 1, and the notation we use is probability P, the capital P, and probability A is of something that is happening for event A. The example that I gave about 100 cars is called empirical probability, meaning that I had some data and I based that probability based on that data. Theoretical probability is something that is, you factor in all possible outcomes, like, for example, rolling a dice, or rolling a die, or flipping a coin. There's theoretical probability. The law of large numbers is another probability metric, is that it's a long relative frequency of repeated independent events that eventually converge and become an empirical probability. So essentially, it is extension of empirical probability. Most of our probability metrics are defined in empirical probability. This is one of the oldest way of doing things. We do simulation, we have data, and based on the data, we can say the chances of you liking a red car is X. Once again, some terminologies. Outcome in terminology in probability is a particular result of an experiment or observation. You're flipping a coin, that is an outcome. So you're flipping a coin is a trial. The tails or heads is an outcome. If you won tails, that is favorable outcome, the thing we're looking for. The probability is something what we define as number of occurrences of favorable outcome, the tails or head, divided by the times you flipped the trials. So for example, a bag contains 15 marbles, 8 blue, 4 white, and 3 red. A red marble probability is 3 by 15 or 20%, and we denote it in probability metrics. The P in the bracket red equals 0.2. And at the bottom, you see something called inequality. What this means is that it is bounded between 0 and 1. The probability is less than equal to 1, and it is also equal or greater than 0. It cannot be negative. So it has to be bounded. It's just a fancy way of writing bounded stuff. I'm going to pause here and take any questions if you have any. All right. I know this is not the most fun content, but hopefully at least it gets you thinking of how different mathematical concepts are falling under analytics. And most of the times we'll be doing applied stuff anyway. As long as you understand some terminology, you should be fine. So, how this looks into is, the statistics create a model from data to generate a model, and then probability also allows us to generate more data. So that is the relation here, and also allows us to look into different things as well. So, as you can see, most of these things are somewhat related here and there. Another topic that I want to kind of introduce is something called a random variable. And random variable we define as a value, or it's random, meaning that it has equal chance of happening. So for example, if you were tossing a coin, it has equal chance of coming head and tail. But when you toss a coin, there are really two outcomes really you're looking at, right? Like you're either looking at head or tail. So it is based on those bounded distribution function that we put. In other words, it's based on some idea about, we're giving them some options. So there are two types of random variables. One is discrete, distinct. And there is something called continuous. Discrete, number of shoe sizes, for example, 7, 8, 9, 10, 11, 12. You cannot have someone with 105 shoe sizes. It's typically whole number, it's an integer. Continuous random variables are continuum of values. In other words, marathon running, 24.5 minutes, or the rainfall. It's continuous. It could be much longer. So one is whole number, distinct. The other one is the one is integer. The other one is value that takes. It's not bounded. It can go forever. So based on these ideas, we can also do something called probability distribution. And all it is it is looking at summary of probabilities for a random variable. It's just giving you shape of the data. And why and how it is related to analytics is what this is really doing you is that it's kind of telling you how it's going to shape or look. Think about it this way, right? If you're doing analysis and if you have limited data and you want to simulate few instances of it to be more precise on prediction, and at that point, what you can potentially do is use the probability distribution to generate more data. So there are many types of probability distribution. All the way at the bottom, you see some green charts. And depending on what kind of probability distribution that you're looking at, for example, I'll give you some examples. Normal distribution is quite common. Normal distribution is where if you survey 50 people and their heights, that will turn into normal distribution because some people are short, some people are tall, and the height is probably around center somewhere. If you're looking at it more coin tosses, it will be binomial. It will be either heads or tails. If you're looking at more on the uniform distribution, which is, let's say someone's telling you your bus is, the chances of your bus appearing at 7 and 8 p.m. or 9 p.m. is the same, that is uniform, the probability is the same. So anything, the shape of the chart tells you the probability if you want to see it that way. Sorry, go ahead, Adele.
Oh no, just wanted to know, I mean, how different is the normal distribution from the probability distribution? Is there a relationship between the two, or?
Yeah, so a normal distribution is a type of probability distribution, really. So when I say probability distribution, so if you, just to kind of be a little clear on my side, the green charts all the way at the bottom are giving you probability of happening. So what they're telling you is that the probability, for example, let's look at the uniform at the bottom. It is telling you the probability of certain things happening is constant, whatever it is, 0.5, 0.4. In normal distribution, the probability of something happening is very high in the middle and equally low on the sides, or what we call it tails. For exponential, the probability of something happening for the early data is very high as opposed to the lower data. So all of these things are actually probability distribution, but probability distribution of normal, logistic, exponential. There are different types based on the probability.
Thanks.
It's a quite a lot of content that we're jumping in, and hopefully I'll be able to make more applied videos to kind of make more sense of these. But in pretty much, if you understand one or two, it's going to be easy. So the one that common distribution is on the left. The one Adil asked about is something called normal distribution. So mathematically, if we can turn everything into normal distribution, we can be very accurate with our analysis, because it's known, the shape is pretty symmetric, right? We can tell which side is going to be what, and which side is going to be what, and so forth. Think about this way, is that the normal distribution is like, let's say you're always same weight, same height, same, like you never gain weight, you're always fit, you're same body type all the time. And if you wanted to, get an outfit, you don't even need to try it out. You can just say, okay, give me medium shirt, medium pants, size 8 shoes, whatever. That's a known thing. That is almost like a normal distribution. It is, you know the data so well that you can predict easily. But let's say every month you put on 5 pounds or drop 5 pounds, you're inconsistent in your weight, then the distribution becomes a little off. It's not symmetric. And that forces you to be unclear about the data. So normal distribution that you see on the diagram here on the right side, what is telling you is that 68% of the data is either one standard deviation to the left or one standard deviation to the right. And as we will continue to kind of go through the information, we will know why that is kind of important. And the curve that we're talking about here is the distribution. So, again, to Adil's question here is that, if you look at the chart on the left, I'm drawing it out. The best way to understand this is probability is all bounded by 1. So all these under shaded zones are equal to 1, right? So the probability of you having certain value here is very high and certain value is very low. But if you combine all of them, it will say 1. So when they drew the diagram, what they did was like this: 1, 2, frequency, something like this. And they just drew it like this. So anything what we call is under the curve is equal to 1. Now let's look at this and the normal distribution. Normal looks like it is equally shaped, right? So if you do this, it's perfect. Equal 50% here and 50% here. Right? And this chart is what we call probability density function. It will allow us to map it. It will allow us to give visualization very, very quickly. The same thing I'm talking about here is a probability mass function or density function, essentially saying area under the curve, this curve is always going to be 0. We don't go here. So in some cases, we can also kind of come up with saying that what is the chances of you being here? And we can define probability. I'll do an exact math and send you a video later in the week. This is like a course in itself, but I'll try my best to kind of quickly make this point come across sometime later in the week with a quick video through Moodle. But one thing you may want to kind of pay attention is that the symmetry or the shape of the curve will depend on the central tendency or mean, mode, and a median. So maybe try to look at this A and B shapes just by looking at it, and if mean was the blue line, the green line, which curve has the greater mean, A or B? Throw it in chat. So greater means, larger mean. So the mean is always going to be in the middle, right? So this purple line is mean. And if you draw a scale here and like something like this, the mean is probably here, right? So this has A has a larger mean, but standard deviation means more spread out of data. So if it is like this, that means most of the data is somewhere around this row. If it looks like this, mean the data is more spread out. When the data is more spread out, your standard deviation is larger. So A has larger mean because it's just longer, and B has a standard deviation because it's just really, really wide. It goes from 1 all the way, 3 all the way to 13, whereas this goes 1 all the way to 9. The shape of the data tells you something. So sometimes we turn, raw data into standardization or standard normal distribution, and we come up with a concept called z-score, right? So z-score translates that, and the best way to understand z-score is, let me give you a problem statement here, and let me go to the next slide here. Okay, ignore everything on the slide, and let me ask you a question. Let's say you took 2 courses, CSDD 100, and in that course you got 75, and you got CSD 1220, you got, let's say, 80. My question is, which course did you do well compared to your peers? Is it CSD 100, 1100, or 112? Which one is a better score, rather? That's the question. Is there a preference over one or the other? Let me give you some context. Let's say you got 75 on this one. It is 75 on this one, but let's say only the average was, let's say, like 60. In this one, you got 80, which looks like a better score, but the average was 81. So this looks tricky. So, sometimes we have to compare apple to, oranges, and z-score comes into play. So obviously, let's say, you have standard deviation of 2.5, and you have standard deviation of 3. Let's say, I'm just throwing the number out there. We need to compare these 3. We need it. This has its own distribution. This has its own distribution. We need to know. 80 looks like a good score, but if you knew that most of the people were getting more than 80 on that course, you didn't do too well. But this one looks like, all right. So we calculate something called z-score, and z-score is x is 60 for the first minus your score is 60 minus the mean is your score is 75 minus 60, that is 15 divided by let's say 2.5, I said, right? So 2.5, let me do the math. It is around, I think, 4 or 5. it was 6 rather. So 6 here. So U z-score is 6 for CST 100, and U z-score is going to be 80 minus 81. So 1 divided by 3, negative 1. So it is going to be negative 0.33. Okay. So the way to understand this is now looks like we are comparative, right? So if this was something like this, your score, z-score, is somewhere here for this scores. For this scores, your z-score is somewhere here. The way we understand this is that you are only better than about 20% of the class, whereas for this one, you are better than 80% of the class. So although the score looks slower, this is actually a better score. So z-score allows you to compare different data. It normalizes stuff. Does that make sense, folks? I don't know if it makes sense, but so z-score always normalizes based on a distribution. So it's always going to be important, rather than saying the first question as an analyst is like, don't go look at the deeper dive into the numbers. This is what we call bell curve, and the z-score I was talking about, 2.5. What this means is, like, we said one of them was 2.5. So you are only worse than around 1% of people. Whereas point -3, you are only better than 15% of the people. So naturally, this score is better because you're doing better than 90% of the people. Okay. So some of the things that we can do a statistical problem is just an overview of whatever we've done so far is, first of all, if you are there's an imaginary company called Acme Kitchenware, and they want you to do achieve their production goals to manage the flow through plant. Each step has a time constraint, and that must be followed as example. And there's a 302 observations and so forth. The first thing you would obviously do is something called descriptive analysis, where you took the sample and you do univariate analysis of the data, mean, median, and so forth. And then create a histogram, create box plot, whatever you identify and see and visualize the data. And this also gives you some idea about the shape of the data. You can also do a z-test to see some of the things that you can do. For example, like you can do z-test to see if you can do if the performance of the factory is going to be good or bad. From the sample data, you can do z-test to compare different records, right? And this is something that, again, I will put some more time next week, is hypothesis testing. I will pause this for now. We'll go back early next week. I think I don't want to rush through this. This is actually quite an intense thing. It takes a bit of understanding. For me, it took me a while to understand it when I first learned this. So I will pause this for now. And this topic we will start next week. We'll continue with this, the hypothesis testing. I will potentially probably also make a little 5-minute video, or maybe if there's content already from someone, I'll recommend you that. But I'll still run through it, and I'll show you how to do it in Python, which the lab hasn't done so. And really, the only thing remaining, and I'm glad that I made a video because there's no way I would have managed to go through the lab together with you. But for Python lab, there is a bunch of things that needs to be done, and the video is already out. You can just watch it, take a break, or do it tomorrow. But kindly do that. But it talks about all the descriptive, distribution, and inferential statistics, minus this part here, which I will pause. I will pause this part for you to show and understand what exactly needs to be done. All right. Okay. Questions, folks? Okay. No questions. All right. So maybe any questions regarding the project and anything else? Yes, Aman, go ahead, please.
Hey, Prof, can you hear me?
Yes, I can hear you. Yeah.
All right, so sorry to bring this up late, but I was just taking a look here on my the submission rubric. It says that we're not a member of any group. So I don't know what to do about that.
Okay, let me quickly. So I'm going to stop sharing and I'm going to stop recording too. And then we can talk about that.